By using the Lipowski et al. Mechanism with formal Laurent series and introducing an order, you can construct fundamental solutions to any, no matter how crazy, if even this and something much crazier. And then you then have to decide on the order beforehand. So you can have one that's essentially here, or essentially here, or essentially here, and essentially here. And if you don't want to play favorites, you can find fundamental solutions in every quadrant, and analogously in every octant, and take the average of all of them. And then you have something symmetric. So this is another proof. And I'm almost sure that you can have a continuous analog of this and maybe use the Lipowski et al. Mechanism to do the continuous analog. But this, I'm not sure. So this is the fundamental principle. In 1959, Leon came with another fundamental object. Fundamental principle. And this is a continuation of what I told you about before. So if you have a system, an arbitrary system of partial differential equations. Let's have an example. The Laplacian and the wave equation. Let's make up. It could be as arbitrary as you want it to be. It's easy to find lots of solutions, as I already told you before. You write f of x by z is e to the alpha x plus beta to the power y plus gamma to the power z. You plug it in the first equation, you plug it in the second equation, and you get conditions for alpha, beta, and gamma. And you get a so-called algebraic variety. So in this case, the alpha, beta, and gamma complex numbers first have to satisfy this. And what I'm doing here is very general. So you plug it into it and you get a system of polynomial equations defining an ideal. And the set of solutions is called an algebraic variety. So you can find lots and lots of solutions. But you want to find all the solutions. So there's even a problem in one dimension, reminding you. For example, you want to solve this differential equation. So you try f of x equals e to the alpha x, and you get alpha squared minus 2 alpha plus 1 times e to the power alpha x equals 0. And it has a double root. So e to the power x is indeed a solution, but it's not the only solution. So you need, it turns out, that x. And what Leon did was a far-reaching generalization to PDE, to many variables. But now things are far from simple. And then he introduced something called multiplicity variety. This is a variety, this is a set of points that with a set of polynomials vanish, and certain differential operators. So you have lots of components. So in this case, the multiplicity variety is 1 and d over d alpha 1. So if you look at e to the alpha x and take the derivative with respect to the parameter alpha, you get x times e to the alpha x. Then you plug in alpha equals 1, you get it. So I don't have time to tell you the details. But this is basically the idea behind it. And it's a famous theorem in algebraic geometry called the Hilbert-Nullstellensatz. The set of polynomials that vanish. So you're given a set of polynomials. You look at the so-called variety, the set of points in the complex plane that annihilate this set of polynomials. And you look for all the polynomials that vanish in this set. You don't usually get it back. You get something called the radical of the original idea. But what Leon did was a far-reaching generalization of Nullstellensatz, where you don't get the radical. It's a complete characterization, but you need these extra differential operators. And this can be used to have a far-reaching generalization of this elementary thing from ODE. And I was inspired by this to do a discrete analog. And this was very, very important in my PhD. And thanks to Leon, I got into the Institute for Advanced Study. Because the stuff I did before I knew about Leon was considered in those days very, very, very backward, very, very not respectable. That's discrete analytic functions. But then I saw what Leon did, and I used Leon's fancy approach and ideas behind it, and thus giving a reference to Leon's work was enough to impress the people at the Institute for Advanced Study to get me my first postdoc back in 1977. So I owe to Leon's, and both directly and indirectly, that I got. So let me tell you briefly how it inspired my work and to extend it. So let me tell you these things that, by the way, now is fairly fashionable. Like many other things, I was ahead of my time by 30 years. Now, Laszlo Lobasz, the World Prize winner, who just got, I don't want to brag, the Kyoto Prize, he gave a very long survey article and a lecture on discrete analytic functions, and I considered a hot stuff, and he very generously referenced my pioneering work from way back. Well, there was no way to get in the Institute where I study only studying discrete analytic functions. So, discrete analytic functions are discrete harmonic, but are defined on the lattice. So this is the difference here. So the difference, like the Cauchy-Riemann manipulation, discrete Cauchy-Riemann manipulation. So that's the definition of a discrete analytic function. Okay, this is I minus 1. And if you transpose it, you get f of mn. Okay, so this, what's I plus 1 over I minus 1? Don't tell me, I plus 1 over I minus 1 is minus I? It's minus I, right? So you get f of mn plus I fm plus 1n minus I. This was considered by Duffin, another hero of mine, Dick Duffin, in 1956. And then minus and if you rewrite it, it's under the condition that the contour, discrete contour integral over unit square is equal to 0. So in discrete analytic function, it's very easy to prove both Cauchy's and Morera's theorem. Anyway, this was Ehrenpreis' idea was very instrumental in trying to find